Hi everyone, this is a video basically with the introduction to forces with a couple of worked examples, just to go over some of the things that you've already learned in the Mary STEM videos. First of all, let's recap what Newton's first law says. Newton's first law says that an object maintains its state of rest or constant velocity motion unless it is acted on by an external unbalanced force. So when it's at a state of rest, that's fairly obvious. An object doesn't move unless something pushes it or pulls on it. However, the constant velocity motion case is a little bit more difficult to understand. An example are spaceships and space travel. So objects that travel in space will keep going at a constant velocity because there is no external force acting on them unless they fire up their engines. However, a hockey ball will roll to a stop because frictional forces act on it, which slow it down. Another example is an ice skater. So with ice skating, if you're going in a straight line, you'll stay at a constant velocity until you try to turn. So the turning is a change in direction and hence a change in velocity, because remember that velocity is a vector. So you'll slow down unless you push off again when you're ice skating and turning directions. So another example of Newton's first law is in a car crash. So in a head-on car crash, the occupants tend to continue in their state of motion and move forward towards the head of the dashboard. So that's why we wear seatbelts, to restrain them, and that's why the airbags are there to protect us. Newton's second law says that the acceleration of an object varies in direct proportion to the external unbalanced force applied to it and inversely proportional to its mass. So the first law dealt with cases where the forces were balanced so that no acceleration occurs. So the object either stayed at rest or moved at a constant velocity. However, this second law deals with unbalanced forces and hence acceleration will occur. Some examples are dropping something over a cliff. There is no upward force to balance the force of gravity, which is acting on the rock downwards, and that is assuming that we neglect air resistance. So, with the second law, we can write it mathematically. So we can say that acceleration is proportional to force. So that little fish symbol means proportional, but that acceleration is also inversely proportional to 1 over the mass. So this is how we write inversely proportional. So as mass gets bigger, acceleration will get smaller. However, as force gets bigger, then acceleration will also get bigger. Remember that the unit of force is newtons. So the newtons is the unit of force. We write as letter N. And we can define a newton as the force needed to give a 1 kilogram object an acceleration of 1 meters per second squared. So that basically means that because we know that force equals mass times acceleration, therefore 1 newton will equal kilogram times meters per second to the minus 2. So just recapping, with acceleration or velocity, we can either write meters per second with a slash, or a slightly more mathematical way to write it is meters per second, or meters second to the minus 1. And this form of writing it there really helps when we're dealing with unit conversions. So you can see here that it's all just nicely laid out. So when we need to convert units, we can cancel out some of the units, or do our indice addition and things like that, which can help. Okay, so our first example. Car of mass 2,000 kilograms decelerates from 30 meters per second to rest in a distance of 100 meters. calculate the retarding force required to stop the car. So I want you to copy this down, give it a go, and then we'll go through the solution. Okay, so you might remember me telling you the story of one of my physics teachers that used to shout at us, parameters, formula, substitute, calculate. And he used to also dictate stuff to us, so he wouldn't write on the board, he'd actually read the stuff out and we'd have to copy it into our books as he spoke it aloud. It was very frustrating, but a good skill, and I've always remembered parameters, formula, substitute, calculate as a really useful way to approach problem solving. So the parameters part is writing down what you know and also what you don't know. So we know that mass is 2,000 kilograms. That is a 0, not a 6. We know that the initial velocity, u, is 30 meters per second. We know that the final velocity is rest, so that is 0 meters per second. We know that the distance, x, is 100 meters. We don't know the acceleration, and we want to calculate the force, so we don't know any of them. So we have written down our parameters. The next step is to look through your equations of motion and find an equation that uses the information that you've been given. So the things that we've been given for this is those 4. So the formula we can use is v squared equals u squared plus 2ax. So v squared is 0 equals 30 squared plus 2, we don't know a, times 100. Okay, so we want to solve for a, which means we want to rearrange the equation. So this is where you've got to be really careful with your signs and with your rearranging, and that you remember that you can only add like terms. So you've got to remember everything from maths, from algebra, and solving these linear or quadratic equations. So in this case, let's move this one over to the other side. So we get minus 30 squared, because we're subtracting it from both sides, equals 200, so I've times the 2 by 100, a. Okay? And now we want to get the a by itself, so we're going to divide both sides by 200. So therefore, minus 30 squared over 200 equals a. And I always leave, when you've got like things that are squared, I always leave it as it is and not put it in my calculator yet, because it just reduces the possibility of you making an error. If you just do one calculation at the very end, it can usually avoid some silly mistakes along the way. So we've got this, so now we can put that in our calculator and we can write acceleration equals minus 4.5 meters per second squared. Now acceleration here, we've got a minus answer. Now that makes sense because we know that the car is decelerating, so the acceleration must be negative because it's coming to rest. And that the velocity was in a positive direction, so therefore this tells us that it is coming to a rest. So that's good. If you end up with a positive answer, you've probably done something wrong with rearranging the equation. So we've worked out our acceleration and we want to know the force. That's what we're actually trying to find. We know the mass, so we can use force equals mass times acceleration. So therefore F equals 2,000 times 4.5. And I'll put the minus sign at the front, which equals minus 9,000 newtons. Now, the force is minus 9,000, negative 9,000 newtons. And this also makes sense because it is bringing the car to a stop. However, the question says calculate the retarding force required. So it already knows that it's bringing it to a halt. Like, that's what it's stating by saying retarding force. So when you answer the question, you can leave it like that, or you can probably good to answer with a sentence as well. So you say, therefore, the retarding force is 9,000 newtons. So we don't have to put the negative in because we're stating that it is a retarding force. If we just said the force required to stop the car, then we would say is negative 9,000 newtons. But because we're already defining it as the retarding force, we can just say it's 9,000 newtons. Okay, so now we're on to Newton's third law. So this says that to every action there is an equal and opposite reaction. So that means that forces always come in pairs. So if a hammer exerts a force on a nail, the nail exerts an equal and opposite force on the hammer. It has to be an opposite force, otherwise it just doesn't work. So if you lean against the wall is pushing back on you, otherwise you would fall through the wall, basically. So we can call these action-reaction pairs. So here are some examples. Action. Exhaust gases come out of the rocket. The reaction will be... Have a think about it. Fill these in, think about them all, then we'll go through it. Okay, so the first one, exhaust gases coming out of the rocket. So the reaction will be the rocket moves forwards. Hopefully you can read my writing. Next one, a sprinter pushes on the starting blocks. So in order for the starting blocks not to move backwards, for them to stay in the same spot, they are kind of held down, but that means that the blocks push on the sprinter. Blocks push on sprinter. A tyre pushes on the road, so road on the tyre. The road will push on the tyre. Oops, push out. And the last one, a softball is hit by a bat. So the bat slows down as the ball pushes back. There's some other ones like an orbiting satellite is attracted to the Earth, and so the Earth is attracted to the satellite. Okay, so our final example for this video is drawing a free body diagram of a box of biscuits sitting on a table. So a free body diagram is just a diagram of the forces. So this is going to be a little bit difficult, but I'm going to try and draw a table. Okay, here is my table. And then I will draw my box of biscuits. There. Now I'm going to mark, say, the centre of mass. Oops. So there's the centre of mass of my box. So the box isn't moving. I'm just going to call this box of biscuits the body. And it's not moving, it's not sliding, the table is perfectly flat, so it's not in motion. So the forces are balanced. We have the weight force, or we can call this force W, body or box on table. And then the other one, I'll just change colour just so you can see it properly. It's going to be equal, so try, when you draw these, try to show that the arrows are equal. I mean, you don't have to measure them, but just make sure they're roughly the same size, that one's not tiny and the other one bigger, because that implies that the forces are unbalanced. So the other one is the normal force, so F subscript N, and that is also the table on the box or on the body. Okay, so that's all you have to do there. And that's the end of the question. Okay, thank you.